Have you ever really thought about the electricity that powers pretty much everything in your life? Today, we're pulling back the curtain on how it all works by looking at two basic ways of wiring things up: series and parallel circuits. And believe me, by the time we're done, you are going to see your phone charger, your car, even your entire house in a totally new way.
So let's just start with a simple question. When you plug in a lamp and you flip that switch, what's actually going on inside those wires? Is the light bulb, using up the electricity? I mean, it sounds right, doesn't it? But the truth is actually way more interesting.
And here it is. This is the big puzzle we need to solve. If you were to measure the electrical current, that's the flow of electrons going into a light bulb, and then you measured it again coming right out the other side, you'd find something wild. The numbers are exactly the same. So if the current isn't being used up, then what on earth is happening?
And that leads us right into our first big idea. We've got to bust this myth of consumed electricity. The way we talk about it can be really misleading, and getting this right is the key to understanding everything else.
Okay, here's the secret. What we call a consumer in a circuit, you might see it called a Verbraucher in German, like in our source material here, it doesn't actually consume the current, not at all. Instead, it takes electrical energy and it converts it into something else. A light bulb turns it into light and heat. A motor turns it into motion. The flow of electrons, which is the current, just keeps right on moving, totally unchanged. And just like that, mystery number one is solved.
Now, to really get how these circuits work, we have to talk about the force that gets that current moving in the first place. And that brings us to voltage.
The easiest way to think about voltage is just as the push or the pressure behind the electric current. It's what gets those electrons up and moving through the wires. We measure it in volts, and you'll usually see it represented by the letter U. It's really simple. No push, no flow.
But here's a little twist. The push from a power source, like a battery, isn't always the same. And that's where we got to talk about two different measurements, something called no-load voltage and another called terminal voltage.
All right, so first up, you've got no-load voltage. This is what you measure when the circuit is open, meaning nothing's actually connected and running. It's the battery's maximum potential push kind of just sitting there ready to go. So in this example, it's 9.26 volts. But the second you close that circuit and something starts running, the voltage you can actually measure drops. This lower value is the terminal voltage. Look at that, it's fallen all the way to 7.39 volts. So, why? Why does it do that?
Well, this quote from our source material explains it perfectly. The battery itself actually has some resistance inside of it, so a little bit of that push gets used up just to move the current through the battery itself. That's why the voltage that's actually available for the rest of the circuit is always a bit lower once everything gets up and running.
Okay, now that we've got a handle on voltage and current, we can finally get to the main event. First up, the series circuit. And the key thing to remember here is it's all about one single, unbroken path.
I mean, the definition is pretty much in the name. In a series circuit, every single component is connected end to end, one after the other. It creates just one single path for all that current to follow. The classic example? A string of old-school Christmas lights.
And because there's only one path, that leads to some very specific rules. First, the current is the same, absolutely everywhere in the circuit. I mean, it has nowhere else to go. But the voltage, that push from the battery, gets shared. It's divided up among all the components. So each light bulb in the string gets its own little slice of the total voltage pie.
So, why would you ever use this setup? Well, the main reason is when you need to increase your voltage. If you connect batteries in series, like the ones in your TV remote, their individual voltages add up. Two 1.5-volt batteries give you 3 volts, which is the higher total voltage you need to power the device.
All right, now for the other side of the coin. If a series circuit is all about one path, a parallel circuit is all about giving the current choices.
So in a parallel circuit, the wiring is totally different. It's branched. This means the current flows out of the power source, it splits up to go through all the different components on their own separate paths, and then it all joins back together before it returns to the source.
And the rules here? Well, they're pretty much the exact opposite of a series circuit. In a parallel setup, every single branch gets the full source voltage. That is the most important part to remember. The current, on the other hand, is what splits up. The total current leaving the battery is just the sum of all the currents in each of the individual branches.
And this
This is where it all becomes super relevant to your daily life. Your house is wired in parallel. This is what makes sure that every single outlet provides the same full voltage. It doesn't matter if you plug in a little phone charger or giant TV, they all get the proper push they need to work right.
All right, we've met the two contenders. Now it's time to put them right next to each other for the final showdown.
And here you have it, all laid out. For series, the current is the same everywhere, but the voltage divides. For parallel, it's the total opposite. The voltage is the same everywhere, but the current divides. And check out the resistance. In series, you just add it all up. More bulbs, more resistance. But in parallel, because you're adding more and more pathways for the current to flow, the total resistance of the whole circuit actually goes down, which makes it easier for current to flow out of the source. Kind of weird, right?
Let's make this super real. Think about those old holiday lights again, a series circuit. If one of those tiny bulbs burns out, the whole single path is broken, and every single light goes dark. Ugh. But in a parallel circuit, like your house, you can turn off a lamp in the living room and the TV in the bedroom keeps on working just fine because they're on their own independent paths.
So that brings us to the big final question. When you really look at how you live your life and all the technology that you rely on, which one of these two types of circuits is the real unsung hero of your day-to-day?
And the answer, by a long shot, is the parallel circuit. It's the design that makes our complex, modern world possible. It guarantees that every single thing you plug in gets the same consistent voltage it was designed for, all at the same time. It's the invisible framework that's literally powering your life at this very moment.